Welcome to the tutorial. The title of the tutorial is Mechanisms of Universal Turing Machines, Vision, Audition, Natural Language. APFGP means Autonomous Programming for General Purposes and Consciousness. Provide the outline, tasks, modalities, history of AI, history of deep learning, universal Turing machines, emergent universal Turing machines, auto-programming for general purposes, motivations, experiments, conscious machines, Brain Mind Institute, and Genesema. Talk about tasks first. Let's look at the task examples. Maybe you have many different kind of tasks, and AI face those tasks. And first type is vision guided navigation example. Not just using laser scanner, we use video cameras. Audition, not just speech processing, may deal with different kind of sound like thunderstorms and bird chirps. In the natural languages, understanding not just language processing. We may also have pattern recognition, various types, and we may familiar with games, but games are considered clean problems, and many don't consider them as AI problems anymore. So suppose we have a vision guide navigation, you're driving, and maybe you have pedestrians, you have cars, you have traffic signs, and you may have car shadows, and there are so many different components of things that you need to pay attention to, depends on the purpose, the context. Here is an experimental setting where we have a single person using vision guide navigation. Basically, a machine is consists of mobile phone, and human control the actions through a joystick, and a single camera looking what it sees, then through wireless connection to the cell phone. So one possible application is worker assistant. You need a real-time computation, object detection, and you need to also decide where to go with GPS telling you the long-term goal, but long-term goal may not be consistent with the local setting because the obstacles, because the situation in the environment. And there are some restrictions in the experiment. We have a single camera. We may have different holding positions because we may have a detour, like GPS tell you the goal, long-term goal, but GPS from Google Map, for example. If you are interested, probably look at the YouTube demonstration, and we'll talk about the method, how to learn this complex task. And vision is very challenging. And you can see that you may have shadows. See that you have shadows if you just look visually, and if you don't analyze the shadows, and the shadow could be just like obstacles. And you may have cast of light probe, and you may have bad lighting directions. You may have obstacles. You have shadows, you have road, you have lighting changes, you have obstacles. So vision is really hard. It's great vision challenges. And look at the concept that's evolved. You may have cars, you may have crossing pedestrian, you have traffic sign, what object is, where it is, and where it is depends on also their purpose, your direction moving. If you're going to collide, you start pay attention to, otherwise you don't. For the what, if it's a cast shadow on the road, you don't really need to pay attention to it. But if it's really obstacle, you need to stop or avoid it. And it has to do with the scale of the object. You may have a boundary of the road. The boundary may not be very clear, right? And you may have detours. So regular navigation may not be appropriate if you see a detour sign. And you may have distractors, like 11 cars that will not collide with you, will not be in the way. You may have buildings, you have shadows, you have pedestrians that are not going to cross your driveway. And the goals is direction to head. This is from GPS, for example, or from map, human read map. Then you may have obstacle in the way, and you want to have detours. You avoid maybe crowds, and you will then determine the current direction and how fast you go. Another example is that vision guided navigation may involve parking. Right? You need to find a spot, right? Those spots are available. Then you need to decide to get in and how to get out. So there are vision issues. There are also goal issues. All those are learned, and we'll talk about the method in the later part of the tutorial. Another example of task is the audition. You may attend a speaker, you may attend to other speakers, you may look at lips and nose. So it's on the fly, you need to change. Without attention, you will not be able to get information from the key components you need to pay attention to. So audition is an example. All right, so audition, not just listening. Maybe visual lip reading is very useful. So audition, in our example, we do audition only, but if you have a multimodal integration, then attention is related to vision, and also for audition in the sense that I pay attention to music or pay attention to voice, speech. So here example that we have a phoneme, and the phoneme lasts maybe a second, in this case O, and has different components of the phoneme, and you need to generate context because this is like 20 millisecond frame. Then if you don't have labels, for example, you don't know this is a class label until here you know the class label. The class label may not last long enough. And then you have silence coming in, you have silence here. And how do they generate dense labels? And we talk about that later on. Why do we need a dense label? Because you want to know that I hear part of the sound, and that's a context, right? Because the context of the sound will be contributing to the label here. So the label provided by human typically sparse, but the machine to generate dense labels, and we'll discuss this issue. The third task example is natural language understanding. Example, suppose that you use mother tongue, learning mother tongue, you may have a bilingual environment, English, French, and you may have a dialect, right? And dialect is not a standard language, but baby can understand, children can learn. Then you have sign languages. Right? For example, the American Sign Language, you have a sign, like it's called printing. and you need to learn mother tongue. It's different from other work stream, but for translation, and we are talking about learning mother tongue. And another kind of learning, basically learn the second language after you become an adult. And the second language position is for mother tongue. And the second language is very different in terms of because the orders learning are different. Then if you have two languages issue, now we'll explain better how to do this. Suppose we have English and French, then here said I don't have time, je n'ai pas le temps. So basically you need to generate those labels. That label is equivalent in terms of meaning. For example, suppose that you have like the Q1, that's English, French, but they're equivalent. Right? You need to have a semantically equivalent state like Q5, English, Finnish, Q5, French. They stay the same syntax. In our case, in this case, we generate label by hand. We have not reached a stage where speech sound is connected to language yet. So in this case, with input is a word. All right. So we have learned about 2,000 words, and the total count is about 8,000. And because we have enough noise, and we have 0 errors. All right. So it's really understanding. All right. It's not like the NTuple using language processing. I mean, not understand the whole sentence, but our case it is, all right? Then if with noise, we have like 0.02% of error. Okay, move on to modality. What do you mean by modality? Modality is a particular mode in which something exists, experienced, or expressed. And sensory modalities are motor modalities. Sensory modality is vision, audition, touch, smell, and taste. Motor modality including like speech, dance, walk, learn, swim. One issue is very important. A brain must learn from its body. And we thought that we probably through programming, you will see in this tutorial that many programming is on track. So we really need to look at how machine can learn. So in this case that we have a robot body, and we need the body to learn. We'll get to that later on. So look at the history of AI. Natural intelligence has been around for many years, and from Socrates, Plato, and later on we have Luhmann and McClelland. They play a role in modeling human behavior using neural networks. Artificial intelligence didn't start till 1900s, where we have first computers, and Alan Turing was considered a father of the AI. So there is a fragmentation in AI and in natural intelligence, and also fragmentation between these two disciplines. So in natural language, in the old days, they started without computation, mainly qualitative. Artificial intelligence is a computation, but little neuroscience. Alan Turing's paper, 1950, he mentioned neuroscience, mentioned psychology. So I like this paper. And it's pretty wide, but he did not have a method how can deal with AI. So he proposed something what we call later Turing test. But that's considered the first paper in AI. But after 1950, we later comers, we start to study AI, but many different approaches existed, and one approach for different kind of problems. So we have a severe problem of fragmentation within AI. And the same thing may happen in natural intelligence. But natural intelligence has a brain to work with, although psychology and cognitive science use a very different approach to deal with human behaviors. But in terms of neuroscience, the situation is slightly better because we have really something, a brain to look into. But many people spend the entire life on just one or few areas of the brain. They are happy with the piecemeal explanation of the brain. It's like brain is totally determined by inheritance. It's like gene. Steve Pinker said that brain area is like organ, like digesting system in the body. And I think that's wrong because the digest is different in terms of chemicals, right? You have different stages, you have different chemical components to deal with. But brain, you have signals. So brain turns out to be using very systematic approach for signals, and I'll get to that later. Some neuroscientists like Gankar, and he agrees that there are a general organization principle in the brain. And so, so there are controversies going on in the natural intelligence. And in the past, natural intelligence we're not really doing too much about what's going on in AI in terms of the logic example. And also other way around, AI people don't really look into brain other than people in neural networks, but the neural nets we are familiar with are not really what the brain is actually, very far. For example, convolution networks so far from what the brain's doing. And I'll get to that later. So there's a severe problem of fragmentation. All right, look at a briefly history of AI. And Turing machine was a theory of computation proposed by Alan Turing in 1936. And about 14 years after, Alan Turing wrote another paper. He raised the issue, can machine think? And he has an imitation game later called Turing test. And the field at that time already have two schools. People said that neural network kind of late. No, it's not true because Alan Turing talked about neural network in that particular paper. And people started to do neural network a long time ago. So these two schools are very much in parallel. I talk about what definition, what the major difference are between these two schools, all right? Symbolic and the Connectionist. And now we are at 2020, so 70 years after, AI has been largely in a wrong track, on a wrong track. What do you mean by wrong track? Many programming. Many of us think that we can build AI system by program machines according to particular task. In the old days, we do not know how to do this, then okay, but the system brittle. But this tutorial will be very different from other tutorials, all right? So 2018, I proposed something called APFGP. So basically that learning must be fully automatic. Humans are relieved from programming for task-specific machines. And that paper was rejected. 2018 and actually 2017, it was rejected by Science Nature. And I ended up posted on AIXIV 2018. And also this conference, IJCNN rejected 2019 and 2020 and also rejected. And I really thank the organizers. I don't want to mention the name, and the IJCNN organizers, and they have a vision after I complained it. Originally, they said that you cannot have two papers. When on theory, when on experiment, it will not acceptable. People are used to like put things together. So at 2020 IJCNN, I have one single paper that talk about both theory and experiment. Of course, the page limit is merely limited, and I have to really condense material into a single paper, but still rejected. And after I submitted complaint, appealed the decision, and I really appreciate they finally reverted the rejection. So if you're interested, you should pay attention to read this paper. That's only 15 pages, but it talks about APFGP. First publishing conference about APFGP. There are some workshops, but only mentioned it and not much. And what is really, really exciting is that APFGP will lead to conscious AI. So in the title, I slightly modified it and apologized. Originally, I submitted tutorial without consciousness in the title, and I think that we should mention it because that's a revolution in AI. So conscious AI will be possible, but this paper also rejected by Science and Nature. Currently, I'm still appealing to Nature, and Nature has a appealing process and Science doesn't. And I'm still appealing at this point, but I have decided to post it on AIXIV. And I really like AIXIV. It just reviews some format, make sure that you don't publish too much, and maybe you don't duplicate your publication at AIXIV. But they do not do censorship on science. They don't. So that's opportunity. You can put your important work there, and then you have timestamps in the history. And in China, this is impossible. It's impossible that you have a site without censorship on the content. So I really thank United States and other developed countries to have this platform, AIXIV. But I will not talk about too much on the consciousness, and that's another talk issue. If you're interested, you can take a look and read it, and I welcome for your input. So we talk about the symbolic schools. Symbolic school, you handcraft the symbols. So you design the symbols, so it's logic, it's clean, because you designed it. And in the 20s, like 1995, in the middle of 1995, we have a common sense knowledge like SEC, and try to put common sense knowledge into a single system, handcrafted. And I think that's a wrong track. Government, US government like DARPA funded them a lot, but I think it's wrong track. It's a lot of money, it's like 10 million every year. Because it's very difficult to use. The symbol, the system did not understand the symbols, and how can you use it? So DARPA program manager told me that it's very difficult to use. So, but government has to really fund some kind of AI work. That's an encouragement, but it's very unfriendly to the users. Then we have a Connectionist School almost the same time, and Marvin Minsky said that it's analogical and scruffy. Scruffy is like dirty, It's like black box, you don't know what's going on. So that opens to fraud. I will talk about fraud, all right, a little bit. And then we have a deep learning network, and we have a CNN, we'll talk about it later. And then now we are at the 2020, all right? This is the first year, the 2020s. And I think that these two schools can be unified because the APFGP, the neural net we have, will have brain-like logic. And the logic, the handcrafted in the symbolic school, will be emergent from experience. You don't handcraft it anymore. So I think there is a very exciting future for AI and the neural network. That's a unification under the framework of APFGP. So look back, all right, we learned a lot from our pioneers. And one of the pioneers I really respect is Professor K.S. Fu in Purdue University. And he was dealing with syntactic pattern recognition because syntax was not really absolutely successful. So you need to have those statistics. So example, it's like you have E with the very different shapes. Then you have H, you have also H, they are linked through a tree-like structure, all right? And because it doesn't fit very well, you have a probability. So that's called Symbolic School. Symbolic School always have probability. Later on, we have like reinforcement learning, still symbol-based. So by definition, when you buy Symbolic School, you handcrafted symbols based on the task. There's a specific task. Oh, from the task, you have a set of concepts you need. Then we design the concept that's static, right? Written as a symbol, like S1, S2, blah, blah, blah. And you define the set of symbol as an S, and you only use that one as a domain, like WordNet, all right? Net is a little larger, but they have a bunch of words. Then you have logic on the symbol, all right? So give example, you have a Markov model. I'll talk about Markov model later on. Then you have a task nodes, you have a goal nodes, you have a purpose node, you have a context node, you have roles, feature, many, many things, all right? They are brittle because if you have a system handcrafted set, but I look into a situation that none of the symbol really fit very well, the system fails miserably. All right, then neural network claimed by many to be more robust or more resilient to failure. And let's look at it. One example that I like to review is by Kunihiro Fukushima. So his goal, now remember, it's always still from goal, even neural network, until I talk about APFGP. Right? So you start with the neural representation 0 to 9. Then you assume that you have only one isolated number, all right? And maybe location slightly different, but scale is roughly right. Is roughly right. Then your features, then you do convolution, all the position here, maybe a horizontal edge, then a vertical edge, diagonal edge, all that, all right? Then you do convolution inside. Then Fukushima said, hey, I need to do edge grouping. So he handcraft the features, all right? This feature, for this one, I need that, and for this, I need that. So I start to have a features grouping. And how many features he need, that's handcrafted. It depends how many features he saw he need. So he look at the test data. If it's a failure, he go back maybe to merge some features, maybe to add more features. Then this another is called simple cell, complex cell, simple cell, complex. So simple cell in his case is basically matching, convolution matching, right? So maybe this is one feature. This is one feature, this is another feature, maybe share the feature, do convolution again. Convolution means apply the same pattern at different locations, right? Every possible location here. And this is feature 1 at different locations, feature 2 at different locations, and so on. And after that, he select the grouping again. Again, and how many you need, can craft again. And keep going until this is a feature of number 0. At feature number 2, number 9, and the location is the way you find that number, right? So in his case, he said that you have a simple cell, complex cell, this is static, 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 and this is from convolution, convolution, convolution. So connection is available over here. All right, so there's some learning going on. It's more like memory learning. And the fixed interconnections because the hand, Fukushima hand selected. Right? Now we said that we must auto-develop. So idea is that we cannot have a fixed task. So we start with a workshop on development learning 2000, and then after the workshop at the Michigan State University, we 6 courses with me, and we published small policy foreign piece in Science. It's autonomous development by robot animal. The key idea, which is really, really new, is that learning must be task and specific. And a single network like genome-like DN, Developmental Network, is only 2 pages long. And it simulates the function of genome. So suppose in human you have a like zygote, right? Then you have a prenatal development, then a postnatal development, you grow into an adult. So that's body development. But mentally, machine can do mental development without doing body development. Body development is still possible, but it's hard. You know, you grow a leg, you grow an arm, it's hard. My position is that body design is a clean task. You really don't need much in terms of design a hand or whatever, unless for specific, very complex manipulators. Otherwise, it's a clean task. Then we really need to do development because the brain task inside the wiring is a muddy task, very, very muddy. So we have ICDO conference, International Conference Development Learning, then we have AMD technical committees, then we have other things like transactions. But very interestingly that as soon as we published in Science, and the US government posed new funding to me, but they found instead my colleagues in the field on traditional machine learning. And we're going on, we have to really move ahead without government funding. Some companies like Microsoft and Toyota funded us. That's also a small amount, but I really appreciate it. It's like change the story. Typically, government should fund fundamental research. Industry should fund application research. But suddenly, the changed. Companies funding me for fundamental research, and the government stopped funding me. I will talk about later on. Something's really, really strange going on. So our system here, WWN1 and WWN9, I'll mention that later. And now we have APFGP, like 3 years ago. So what is APFGP? Autonomous programming for general purposes. So you have a machine that can do programming inside the brain, totally autonomous, and for general purposes. The purposes the programmer does not know about. Like you know a math or computer science, and your parents never learned math or computer science. So a machine should be able to do autonomous programming, like design mathematical procedure or write a C program. Inside the skull is fully autonomous. I'll talk about later. And the skull must be closed entire life. Outside skull, you have nature, and you may have teacher. Teacher may is a part of the sensory environment and give you information from vision, from audition, from touch, whatever, but teacher is a part of environment. Then look into a history of deep learning. More detailed, we talk about deep learning only because deep learning is hard right now. Paul Wolbers, as early as 1974, he published error propagation for neural networks, a very early work. And I think that error propagation based on gradient descent method amounts to fraud. So, but I put a question mark. I just asked people to discuss it. Then Fukushima, we had a neural Connectionist. It's a for 2D pattern, not 3D monolithic. Then at that time, 1991, I finished PhD and I went back to Illinois and I like to do something very different from what I have been doing in terms of motion and structure from image sequences. We had a paper, we had a 6 papers, IJCNN transactions, but then we had a book published by Springer-Villach. And the title is Motion Structure from Image Sequences. But from this point on, I start to, basically 1990, I start to do Cresceptron. Our goal is to learn from 3D world without 2D model, without 3D model, not at all. So first deep learning for 3D world and for cluttered environment. So Professor Thomas Huang said that Jiang Wen was ambitious. We have 7 new ideas. I'll talk about new idea later. And blah, blah, there are many deep learning guys that you're familiar with. All right. Then we have an ImageNet, popular now, but I claim that it, data falsification and made misleading claim to exceed human performance. I'll get to that. Then 2004, Google founded DeepMind with 400 million. I think that's something like no-brainer. Suddenly, money is here, big money. So deep learning suddenly becomes hard, right? Deep learning becomes hard, but I claim that plagiarism of Cresceptron and fraud in the technique from gradient-based method. I get more, a little bit more, right? So it's like no-brainer. It didn't really happen over here. It's still not hard, actually. It's hard when 400 million was invested from Google. Now, what do you mean by plagiarism? And I will talk about the 7 ideas. Cresceptron is the first for all 7 ideas. And many people use the 7 idea and take like granted, take it for granted. It's a first deep learning network for 3D objects. I use red to see the key. It's 3D without any 3D model. And it's first doing concurrent detection and recognition. Many people doing sequential learning, they don't do detection. They already assume location and scale. And it has scale and stride. All right, I'll talk about stride later on. To reduce the resolution, basically. In the large patch, you don't really need to have a fine resolution in terms of location. Number 3, and large scale 3D objects, because if a large object, and it's very difficult to learn and to match well. So you really need to have a hierarchy, a deep hierarchy. All right, many people use the hierarchy now for grounded without citing Cresceptron. Cresceptron is the first automatic built hierarchy for large object. Although Fukushima used hierarchy, but it's not automatic. Later on, the deep learning guy was using that automatic, using the idea here, number 3, all right? And the number 4 is the pairing of feature matching and subsampling. Fukushima used handcrafted features, so he does not need to do subsampling. Cresceptron is the first to do subsampling automatic. Number 5, position blurring. And some people using weighted sum, whatever, this is position blurring. They did not cite Cresceptron. And we use the maximization, number 6. We did not use mass pooling, but somebody like student of Tommy Pardew, they start with Matplotlin, and the Matplotlin name becomes popular. But we create the first idea, number 6. So in terms of importance, number 1 is much more important than number 6. So this is the order, roughly, it's the importance. Matplotlin, nothing without those ideas. Nothing important. Number 7 is segmentation, doing post-analysis. After you recognize it, and you use the reverse logic of the network to find out which pixel contributed to recognition and disregarding the background pixels. And ImageNet did that, but ImageNet did not do polygons. We did polygons. We actually got the pixel level. And ImageNet only used a rectangle, so did not do as well after Cresceptron in 1991, but still did not cite Cresceptron. Maybe they didn't do as many as original as Cresceptron. They chose not to cite it. So here comes, I've only made discussion, all right? I only discuss, I do not really say there's a fact. It's up to community to decide, maybe court to decide. Fukushima, neocognition, Cresceptron, stuff from 1991, and journal version is 1997. By the way, this reviewer of the journal version want to reject it. I really appreciate the editor-in-chief, a Japanese professor at the curriculum, Kanadi, Takeo Kanadi. He called me and explained, said that somebody want to reject it and he has some issue and he'd like to discuss with me. And I really appreciate it. At that time, I was over here at MSU already. And I really appreciate that. I asked Takeo, I said, Takeo, you did not like neural network. How come you liked it? He said that whatever works. So Takeo Kanadi is open-minded. Then Leon Lacon, I use the red means start to do plagiarism. That's my claim. I did not say there's a fact. All right, this is only raised for discussion. 1998, they start to, this is 2D still, but already used the idea of subsampling of Cresceptron. All right, Fukushima did not do subsampling. Pardew and Nature Neuroscience had a paper using idea of maximization, all right, 1990. So that's how many years? This is like 8 years after. And HMax, that's like 8 years, even more. Li Fei, her PhD did was 2005, and she used the idea of, first idea of Cresceptron and others without citing it. And she later published her work in PEMI 2006, added another second author. Yan Lacon started to do 3D. This is 3D, 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 and just 2D, and that's in NIPS, and without citing. And Junin did 3D since ICD. I only say this is 3D, and this uses the idea of Cresceptron 2D. And Jeffrey Hinton, NIPS 2012, started with 3D. And Fei and Google researchers and staffers in CEPR 2014, at least, start to do 3D and without citing Cresceptron. So basically, they cite the work that are not very useful to them, but they don't cite the work that are very useful to them. So if you're interested, watch YouTube. The Turing Awards go to plagiarism. Then I claim that many neural networks are in crisis. So one is problem of the open scale. Basically, you use the data and you start to tune the parameter and the architecture and the structure based on the data. So the network is like cloning from the human intelligence. That's one thing, including work like AOSTM, long short-term memory, and SOM. And then another is a post-selection. They use the test set like training set. And same thing here, all right? AOSTM and SOM. How to avoid them? So basically, how to make it skull close so it's for automatic instead of using human intelligence. And also report only one network over here. Here you have many networks, only report the best based on the test set. And Cresceptron did that. Cresceptron only one network, grow incrementally, and didn't use open skull, did not use more than one network, but not optimal. The end is optimal in maximum likelihood to do that, all right? So this kind of flawed, for this is a flawed open skull, and because of open skull using human intelligence, not really machine automatic recognition. And this is using test set like the training set. And how to avoid that? And we talk about the Turing awards, go to flawed, all right? That's YouTube. Then I'd like to congratulate three researchers, Hidden, Benjo, and Lacombe. They received Turing Award 2018, but I claim they falsified the data. Now, I get you get more detail onto the YouTube, but I'd like to see that our network. We use CAN using random initial gets. We pick the luckiest backpack network. That's over here. This area, the lower the better. And our optimal DN is right there. This is the first epoch of the data. We are already optimum. Area right there, 6 already there, and they're up there, right? And then if you do more epochs, 100, 200, 300, 400, 500, 500 epochs still there, all right? We are here, all right? So that it's luckiest CNN even use so much training, so many epochs, still falling above our optimal. We are optimal first one. This is 500 still not there. So single DNA is always optimum in maximum likelihood. If you're interested, maybe read the paper. So the Connectionist School is motivated by neural-like computation, and many artificial neural nets are symbolic because they use each line like label, all right? There are certain nodes considered as a concept, and they use each line, like responsive neuron, is corresponding concept as a symbolic concept. And the total network lack of logic, it's a black box. And then many people claim that's less brittle. And I don't think it's true, not really. And I get more to that, all right? And I allege fraud in Turing Award 2018 because it's like logic, it's like black box. So the startup people just doing a lot of networks start to tune the parameters to fit the data. So it's not really brittle, less brittle, but just using test set as a training set, all right? So it gives room for fraud. So there are two frauds going on. One is open skull, as I said, human intervention into neural network. It's not automatic. Post-selection, it's not automatic because you just train so many networks, pick the latest one. How do you know in the real application, you don't know the task, you don't know the data, then you cannot pick the best one. The best one is already patched. So that's a crisis, all right? I call limitation at this point. Then now we have logic, right? We talk about universal Turing machine. And Turing machine is based on Symbolic School, but we need to learn it. Then from the logic, we say neural network can accomplish this kind of logic. Very exciting. So the Turing machine, you start giving a task, a specific task. Then you design a Turing machine, right? The Turing machine is tape, each cell bearing a symbol, a schema, and you have read write head, you write the tape, a Q, another symbol. Then you have control. That control is handcrafted by a human for a particular task. The control of the Turing machine is a transition function, and it has called 5-tuple. 5-tuple, remember 5-tuple. Previous state, current symbol you read from the tape. Then the next state, the right symbol, what symbol you want to write onto the tape. Then head motion, left, right, and stationary, right? So each move corresponding to 5 components. Then you start from initial state and initial state symbol to on the tape. Then you start to run until the machine halts here. Whatever left on the tape is the output, all right? So this machine still special purpose, all right? So you write this tape here, this Turing machine here. Now, what is a universal Turing machine? Why it's exciting here? It's universal because the universal Turing machine is still the same Turing machine. Only difference is that you on the tape is not just data for the task, but on the tape, you don't have a task here, all right? You have a task, then it becomes special purpose. Really the task is given by this programmer. This programmer is a user of the general purpose machine and write a program written in the 5 tuples. And or you C language. C language equivalent to 5-tuple sequence, but need a more complex compiler. Then you have a program, then you have data that for the program. So because any program written by programming, it becomes general purpose, all right? Very important, I'll review again. General purpose computer is that in the input, you have a program provided by a user, all right? And how the brain pick up with the purpose, it's still from environment. So suppose this one is from environment, then you learn program from the environment. So later you will see that, all right? So you really learn program from the environment, all right? But it don't have to be symbol. Later we have here we have symbol, all right? Later you don't have symbol, you have vision, you have audition, all right? You have touch, you have smell. All put together becomes a general purpose program you can learn from the word. Of course, each task is special, but the brain can learn any task, all right? As long as you spend time on that. So now we need to expand that machinery, all right? So we can agent FA. So FA does not output state, only output yes or no, accept or reject. So we agent FA, you output state each time, output each time. And a state can be anything, all right? Not just yes or no, but you have action, task, context, all things you can think about it. So state including action, not just context, all right? Not just yes or no, not just action. States are everything. We can agent FA or AFA. Now, then we want to say that control of Turing machine is FA. That's from me, right? I proved a few years back. And I think it's 2015. So you used to have 5-tuple, right? And I just changed the definition so that it has a formulation of FA. There was a reviewer in the National Science Foundation, it's in Syria group. He said, oh, of course, Turing machine is a FA. He did not know. He did not even know Turing machine. Turing machine is not FA. He saw the finite state. Finite memory is the same as FA. No, he did not even have a clue of Turing machine. Turing machine is not FA. You really need to redesign. That's what I hear, all right? So we designed that the sigma becomes larger, including the tip symbol, so sigma prime. Then the state becomes much larger. State has including not just state itself, but also tip symbol, and also head motion. All together become Q prime. Then you can write as like the transition function is Q prime with sigma prime and then Q prime. That's a formulation of FA. So the reviewer, I respect him, but he did not know FA. He just was a lousy reviewer. He said, Turing machines FA, he is lousy. And you need to really prove it, none of the FA, right? That's in 2015 in International Journal of Intelligence Science. Then look at the FA. FA is bad, right? For AI, it's really bad. In the construct FA, typically there are many possible states, and the human tries to prove many states, then it's too many states, like a psych. They really have to look at the states, then merge states, and try and error. That's why they need a $10 million each year. And over 10 years, I don't know, still funded or not. And I like the researchers, but I don't like the project. The problem in the micro world can be a graph G, and FA computation is like a solution in this graph G. You find a solution that's a subset, and you do search, and search can use Dijkstra's algorithm or A-star search algorithm. Many people learn FA without doing search issues, right? But you really look into the really how to do effective search. Now I move to our next section, emergent UTM. Now this UTM is handcrafted. How make UTM to emerge automatically? So we have designed a developmental network, DM, that enable UTM to emerge. And I will compare with symbolic network, right? Let's do symbolic network first. So suppose we have alpha, beta, gamma, you handcrafted, all right? Those are states. They have features. Features may be from images, right? But they have to handcrafted features, A, B, C. Those are the three types of symbols. Then they do transition, right? The alpha, beta, gamma are the symbolic states and the transition. And because the symbols are not good enough, so basically there are inconsistency in the transition diagram. They start to use the probability. So 80% from A to A and 20% from A to B with the same input A. See that? And if you do reinforcement learning, all the reinforcement learning I have learned and saw all used symbolic network, all right? Finite-state machine, just like that, all right? Just have a value, add another value. Value is each state has a value, basically. Use time discount model. Fundamentally different, this is the M. So basically the alpha, beta, gamma, instead of alpha, beta, gamma, you have vectors. You have vector patterns. In this case, I'll give a simplistic version. Then we have scales, this is 3 sizes. You have a number of locations, you have what, a number of types. And easier to see, basically, this is still symbolic, but becomes pattern, right? And this is called vector representation of the concepts here. Then you have images, this is pixels, all right? Then you have a top-down. Did you remember FA? I'll go back to here. FA, you have a like state, top-down, this is a bottom-up. Then you go to the next state, there's FA. We implement this FA, Q sigma to Q. That's Q here, like Z, sigma like X here. Then we need the top-down input, bottom-up input, go to next state. Begin. State, input, to next state. That's time. Time is very important, because this is frame machines. Time 0, 1, 2, 3, 2. And for each column, you can only use the information on the left side. You cannot use information here, otherwise the system becomes, neurons start to wait for each other. This is not allowed. So top-down input, each neuron has a weight here, all right? This is a perfect match. When you don't have enough neurons, they start to have similar patterns will be averaged here, similar pattern like that will average here. And for bottom-up, same thing, have similar pattern like that will average from input will be here. So this neuron can be able to match similar pattern from Z and similar pattern from X. X is for bottom-up input, and Z is for top-down input, all right? Then you can have local views. Local view, I only use the X input, but also can a local view from top-down input, all right? So now you have this one like local view. If this one wins, then you have to pay attention to local patches. Global view is global. So now you have this is a top one competition. Suppose you have 6 neurons, and the ones that match the best will win. I talk about what do you mean by best. Basically, you want to match the top-down match and bottom-up match, right? And when you match best, then you do competition. Competition is extremely important. And gradient descendant method did not do competition. Then you messed up. Gradient only tell you, hey, what can help you? Suppose gradient method, right? There's, oh, what can help me? I want to hide here. Then you want all those guys to help you, but it's not their job. Competition says, this is my job. All those guys, you shut up. It's my job, and I only help him. All others don't. If you have top K equal to 3 or 5, those K neuron will help because that's their job, all right? Like committee, all right? K equals 3-member committee. Right now, this one, we will use competition. Competition is essential, all right? Essential is the competition, and Brenda's competition, we'll talk about it later. Then once I find, I use Hebbian learning, then post-selective firing. Suppose you teach yourself, have this pattern, or you practice yourself, or teacher help you supervise your motor. Then the post-selective neuron firing, pre-selective neuron firing, then you link it. All right, I'll talk about LCA later and talk about how Hebbian learning allow you to compute probability on the fly. So this is the probability condition on this neuron to fire, and this neuron fire. All right, this is a condition on this neuron firing, and what's the probability for this neuron to fire, and so on. What's the probability for this neuron to fire? It does not have to be linked from single neuron. Probably like this neuron, all linked to this neuron. All right. Then after this neuron, this pattern becomes the top-down input for that one. All right. So same thing here. 6 will be firing here too. Then take top-down input and bottom input. All right. So for 1, I only look at the neuron here, so it's not crowded. For 3, only draw a neuron here, and here I draw weights, and here I draw weights so that becomes cleaner. All right, because it's a lot of things going on, and I designed this diagram to be very, very intuitive. So you can see that just from this diagram, you can see that how attention happens. This neuron happen, and they pay attention to that. See that? So attention is based on bottom-up and top-down competition, not like bottom-up, like Christopher Koch, and like his early work about attention, but his attention is bottom-up novelty or saliency. That's not really the real story of the attention. Attention is based on top-down and bottom-up, both match. Then you have attention. Attention, pay attention to that one. So attention is like something that you cannot escape. You think that you are free will. No, you don't have free will. Everything is automatic. You don't have freedom. Very interesting issue. All right. Then in real situation, suppose I have like Z, you have GPS, you have where, location, you have what, you have GPS, which direction to move, and you also have other actions like stop, like turn left, slide to right, or right, left, all those things, and very, very complex here. This is explanation of these symbols here, and look very complex, but simple for a child, right? Simple, a child can run without really telling you the logic. It just worked. Simple for DN too. Simple DN too, because everything inside the DN is automatic. All right. So I redraw this diagram over here. Then I see that this neuron wing, and we go to next one. And this neuron wing, go to next one, and start paying to this. I simplify the explanation so that this input is the same. I call retain. Retain one frame, retain one frame. So you can see the logic more clearly. But in real world, you really don't have to retain. You just real time here. And delay is 2 frames. Is that this frame, you get 2 frames. So minimum delay is 2 frames. All right. From here, you need to update the internal hidden neuron. Then you need to update your Z neuron, actually motor neuron. So at least you need to wait for the hidden neuron to finish computation, you need to wait for Z neuron, motor neuron to finish computation. And same thing going on, see that? And you have invariance. Do you see that? We have invariance because I'll talk about invariance later on. Basically, the same neuron, type neuron will learn different locations. Different where neuron will learn different types. They're called type invariance. I get to that, right? So I can also do segmentation. Suppose that I have like this, all right, this is cheetah, all right? And you have a background here. You see, even I have a small attention window now, and those are the background. So this is the real contour of the cheetah. And this is a neuron that learn from cheetah. How did that one? Because those places, originally, this neuron have weights here, but they don't match very well. When cheetah was firing and my neurons firing, and this is the hidden neuron that fires. And the hidden neuron, look at that, wow, it's bad match. Sometimes you have this background, sometimes you have that background, and don't match well, but this part match pretty well. Then this white will kept, and black area match badly with high variation will be pruned away. So each neuron is doing local segmentation, all right? So at the end of segmentation, the outside motor may not do segmentation very well unless you start to draw a picture, all right? Start picture, you start to do sequential segmentation, but each neuron does do local segmentation. Then we also do invariance in terms of location, because you may have different location in the image. You can have different scale, large, medium, small. You may have viewing angle difference. You may have lighting variations. You may have more than one object. You know, with this object. You may have 2 objects. You may have background, right? All those are automatically taken care of. Then how the machine grow a brain, right? So explainable, right now it's explainable AI. Neural network, it's not black box anymore. It's highly recurrent. That's how it's harder to understand. Highly recurrent in the sense that each neuron has 6 fields. You have a sensory receptive field, sensory effective field. Excuse me. You have a motor effective field. You have a motor receptive field. You have laterally receptive field. All right. You have lateral effective field, 6 field in general. Highly recurrent. And you have brain areas, and then you have like this is type neuron grow ventral pathways. And your location neuron that it grow dorsal pathways. And each neuron here that corresponding to the number Z neuron correspond to this type. Red color is the type, and this is location. You have this location neurons, and then you have type. This is the AB type, and then you have competition between a B. You pay attention to A or B, depends on the competition here. And this neuron 5, this neuron 5, but this A wins. Then you pay attention to A type, or in the B type. Right? There's a competition going on. And also based on the type competition, you can location. And once A wins, then you have location popped up, right? So there's invariance in terms of many parameters like location, type, lighting, and so on. Lighting is like you have object A of this location, different lighting, and you need more neuron to memorize or detect the lighting pattern. How does DN learn relation? Now you have type, right? Still pattern recognition. How do the relation? Suppose like you have a B group, the A B becomes a group, two cheetahs, and you have A plays B, all right? A plays B, and A gives B to C. I get to that, all right? DN automatically builds a knowledge hierarchy. It goes like this. Suppose I already have location and the type. I have A, B have two object, location, two locations. Then I have A, B, I learned, okay, this becomes a pair now, A, B. Then you say a relationship neuron coming up, then this neuron will learn this pair, all right? Then with type, with their location, and other neuron will have connection here to the same AB type, but at different locations. So relation can be location invariant, location invariant. This could be location invariant because you have many neurons that connected to AB type. So this is basically still same in here, except that this is a later neuron, typically called a later neuron in the frontal cortex. I unfold it so they can see more clearly, but in the brain, still like later neuron, all right? It's basically you have a frontal cortex over here, all right? Frontal cortex here. Now, in the experiment, we have a WWN and each N 1, 2, 3, 4, 5, 6 to 9, and we even have a natural language, and each version will have a different function built into it. Then talk about theory. Without theory, we will even have an experiment with results. They really give you insight because you can always tune the data to show that my method is better. Basically, it's tune the data, right? So the theory is very, very important. The control of the Turing machine is FA. Just outline the proof. For the detailed proof, you read the International Journal of Intelligent Science, 2015. And emergent control with Turing machine, and we have a paper that proved that DN can learn the emergent control of Turing machine or FA. And also proved that DN is optimal, right? That 2015 paper proved that DN is optimal in the sense of maximum likelihood if you have enough neurons that do initialization and learning at the learning rate 1. I'll get to that learning rate, attention rate. And the first learning attention rate is 1, then the input directly copy into network, so it's error-free. But when you have finished all the initialization of all the neurons has been initialized, then you don't have enough neurons, then start to do dynamic clustering. The clustering is based on maximum likelihood. It's optimal, right? Conditioned on incremental learning. So our network, even single network, is optimal. Regardless, you have random weights. All the random weights are equivalent. You result in the same network. Very beautiful. The emergent Turing machine is logic complete. If you read that Turing machine logic is complete because Turing machine can model other logic, right? Model other logic, like universal Turing machine. And if your Turing machine with motivation, then you can self-program, try to maximize the value in terms of pain avoidance and the pleasure seeking and uncertainty measurement and also novelty. I get to that later when we talk about motivation. Then we need to have a very important set of properties called Genesema Turing machine. When by Genesema has 8 letters. They are acronyms for GENISAMA. G for grounded in the physical world. E for emergent representation. You cannot have handcrafted representation in the network at all. You cannot open the scale. Natural representation from sensor effect. You want to tag directly these pixels and muscles. You cannot use any special coding because coding method may lose information, all right? Incremental computation, you cannot use batch. So ImageNet, everything's batch. We never do batch, right? And you must incremental learn like you move on your life. you incrementally learn, previous learning can be used for later learning, and the later learning can help the future learning, all right? So the later learned task skills will help the learning of the early later skill will be used for later learning, called scaffolding. Then scope must be closed. Everything must be automatic. Otherwise, you have open scope issue, then it's a flawed. And it has to be attentive. You may pay attention to the parts from the cluttered environment. You must use the motivation, otherwise you have a complete object, but it do not have a value and doing nothing. How about doing nothing? I have a complete logic, but I don't do nothing, don't do anything, right? So emotion is a special case of motivation. You need to also abstract from concrete examples, not just fitting data like a CNN, must also abstract rules coming out, like calculus. Right? Calculus is rule. And then as a control of the general massing, I'll give a simple outline first before I get to the details. So we have Q sigma input, go to next Q with vector now, right? So a sigma X and Z. And a symbolic search will do a top-down match. So basically the top-down weight will match this top-down weight. For symbol, you just search, right? Symbol can be symbol or different, same or different. But for vector, you really can use a vector match. For example, in this case, we use a unified vectors, and in the product, the best match for two unit vector is 1. The worst is -1, all right? And the bottom-up weight and bottom-up input, all right? Then you pick the winner. If suppose top 1, they have an IJ, and the top 1, and because definition of F is this one, then you basically top-down input, bottom-up input. We call energy of top-down match and energy of the bottom-up match. In practice, actually, we put a weight there. We have a top-down weight and bottom-up weight, and then we multiply that one and add together, 2 weights together becomes 1. Then top 1 can be like 20%, bottom-up like 80%. Right? All right, go to the CCI PC. And we do PC is because the it's based on the local component. I'll talk about later. So PC is very, very useful for finding features. And we use incremental computation of the mean. We use a subtract mean incremental computed. We have like scatter, each one coming in. Then we do, this is a unit vector and input, we get a response. This is basically, it's a linear in product response. Then we have response weighted input. Then this is the old weight, this is a new weight. Then this is a learning rate, retention rate, scalar, and learning rate in our default case is 1 over time, which is the age, t is the time. And the retention rate is 1 minus the learning rate. But we add this positive so that if this is 0, then it becomes straight average. But early baby learning experience not very useful. So we want to add this one a little bit larger than 1. Given example, this one could be like 1 or 2, and change with t, so that you pay more weight to the new data. So the old experience gradually forgotten, all right, but not drastically. Then we, for PCA, CCI, candidate covalence-free incremental PCA, we subtracted so that this becomes residue. This one is always, this subtract residue is always orthogonal to all the VIs. So the next VU will be used for the next PCA. So that's how very complex computation of the eigenvalue of the principal vector and principal vector and principal eigenvalues, principal vector, which is the eigenvector, and the eigenvalue, which is the scalar. We don't even need equivalence match. In this case, we just come in with a vector. We just come in with a vector. And we compute already the vector coming in sequentially. We already compute the PCA, which is V's, right? V already computed incrementally. Then we change the PCA to DN, all right? So we give up that all the U has to be orthogonal, right? And V vector does not be orthogonal because brain really don't need to be orthogonal. So then we have LCA. DN algorithm, DN1 algorithm, and very similar to the PCA. We have 3 areas now. We have X, Y, Z. They have a vector of the neuron weights and the age, for example, the network structure. And the every area X, Y, Z compute in parallel. And X, you don't have to compute if you don't predict X. Z is output. Hidden area is Y. And every area perform computation. Then it may need to do like initialization. If the match don't very well, we can mitosis generally new neuron, for example. Then we compute the area function of the bottom-up input, top-down input, and then we get the response and a new updated network H, for example, N. And the area function is like that, just like we did before, except that we just use differentiation. They have a unit vector and a unit vector P, and this part is the top-down input. This is the weight, this is the top-down input, and the bottom-up input, bottom-up weight. And after, if suppose the 50% weight, then you have inner product, we get response, right? Then we do computation just like we did before. Find the top K. If K equal to 1, just find 1, and suppose you have C neurons. Everywhere compute like that, all right? Then you do Hebbian learning, response weighted input. Then you have learning rate, you have retention rate, old weight, new weight, updated. Then after you do this, so you can prove that the weight is suppose that WI is 1 over N, and I is the neuron age of J. Each neuron has its own age, all right? Then you just doing this way. And if suppose you do not have a positive vector value to make it larger, to weight more of new data, then you can compute, you can prove that this way you get average of the input. So V is like representative of the Congress. And the P's are the voters in the Michigan. And add together all the voters in the Michigan, I have a congressman for Michigan. It's incremental dynamic clustering. And the boundary is based on, it's not really a static boundary of Michigan or Ohio. It's the dynamic determined boundary based on the nearest neighbor, because computation is based on inner product. Now move on to automatic programming for general purpose, APFGP, all right? So why we use APFGP? Because all natural intelligence use APFGP. And for animals, start from zygote, embryos, fetus, newborn, infancy, and adulthood, lifelong experience. And behavior of the baby becomes more and more like law-like. So we like to ask, what is the minimal set of APFGP the brain is doing for a lifelong learning? Minimal set means set of mechanism. I get to that, all right? This is something that we did not really think about it. I let you know that we already have a solution. We computed 2 kinds of learning mode, all right? One is mode 1 is simpler. It's learning from a teacher Turing machine, supervised. Basically, you want to simulate the transition of Turing machine. So it's like a simplified toy word, all right? If we learn that when toy words start to have variations, then we look at more general learning, which is learning from real physical word without any explicit teachers. I'll give you an example, right? Suppose I have like, all right, this is 1, all right? This is another 1, And this is another one. Then you put together 1 and 2 is 2, all right? This is 2, all right? And 2 and 1 is 3. Do you see that 3? How would it mean 3? 1, 2, 3. Just count 1, 2, 3. Then you can have another 3, right? You have other 3 objects. Then you have a 3, 1, 2, 3. Then later on, 1, 2, 3 becomes abstract, right? Become type invariant. It's a number. That's how generalization takes place. And there are a lot of papers talk about they call developmental learning in psychology. So mode 2 is learning from real physical world. And we just learned a simple one. I teach a TM, right? But later on, you'll see that the learning takes place automatically, generalization. So let's talk about the mode 1, then we realize that the mode 2 generalization is automatic in the lifeline. Theory 1, the control to the emerging is not an agent FA, but also attended agent FA, because the read-write head attends. Theory 2, the learning from the TM, regular or universal TM, through patterns, mode 1 or 2, with top 1 finding in Y hidden area of the brain. The DN control enabled a learner Genesema Turing machine to emerge, really emerge, an emergent Turing machine inside the DN with following properties. When you have sufficient neuron, it's error-free. Insufficient neuron, it's optimal in the maximum likelihood. So it's very similar to the theorem we talked about earlier, except right now we talk about the learning Turing machine now, right? Theorem 3, a Genesema Turing machine inside DN automatically programs for general purposes. Now, automatic program for general purposes. For a number of purposes, after it has learned a universal Turing machine. Now we talk about Turing machine, not FA anymore. And the related purposes, because you really need to know the purpose. Like I know eating and I can eat. Learn eating from my purpose of eating. Later on, I do calculus, then I learn calculus for the purpose of calculus, all right? So the purpose may change through lifetime. The DM program itself is task independent and the language independent, because the DM program does not have a task, did not have a language either. You can learn English or Russia, because we did not have language. We only have DN top-down match, bottom-up match. We do not have the 5 tuple for symbolic TM either, right? So that's a problem. Suppose give them how it takes place, all right? Suppose have a FA like that, all right? So output is yes, this is yes, double circle yes, single circle is no, all right? Yes, yes, no, no. And this is transition, and a simple one, all right? So this is a transition diagram or lookup table. The state ABC, input 0, 1, 3, 0, 1, 3, and this is the A with 0, you get A, B with 1, go to B, go to state, all right? This is very, everybody all of us know, right? In computer science and in neural network, in control, they also know. And this is a symbol. We change this one to muscle. We change it to pixels. We change all those types to muscle. Aha, that's the way. So once we have a pixel to muscle, we emerge in FA. So from this one, it's really difficult to see what's going on. With symbol, we understand, but we don't understand. Maybe we have a lot of pixels, a lot of mixels. Then let's see what happens. So we live now, right? So this is Z, muscles, X is pixels. First state to start with, whatever the state you default to this fine. Then you have Y corresponding to funny neuron. This is a corresponding neuron. But for FA, do not have internal representation. We have Y a first, Y one neuron. Then we have practice, we have next input, Y2 corresponding to this transition. And we have a next one coming out, we have action, we have you swimming, for example, and we have Y3, Y4, keep them. This is lifelong learning. So DN wise and adapts automatically and incrementally. Go on. So let's have discussion. We have solved a series of problems, very, very important problem. Each problem is $1 million. Without solving this problem, single winning problem will not be solved on its own. You really need to have multiple $1 million time solved together. Solve the nonlinear problems. Like in control, we have nonlinear control, highly nonlinear Turing machine. We solve local minimum problem because we have optimal, highly nonlinear optimal. It's optimal in the sense of maximum likelihood. When single network only, we don't use post-selection. And the DN2 have white-to-white connections, so it becomes higher order Markov model, all right? For better context, better learning. And later on, actually, it's just when it learns, it has its own purpose. It's really thinking. Thinking is automatically formulated in Turing machines, emergent Turing machine. Okay, look at the motivation. Motivation, we have a serotonin, there's pains, and dopamine have pleasure. So we avoid pain, we seek pleasures, but these two are new, all right? This is acetylcholine is expected uncertainty. It measures the uncertainty in the variance, basically, all right? Nerve reference is called NE in biology, is estimated novelty. And those are the neuromodulators that are released to estimate the pain, pleasure, uncertainty, and novelty. And we use uncertainty and novelty put together to decide how to grow. If the novelty is low, then we can keep them. If novelty too high, we'll prune them, all right? Okay, talk about experiments. We already talked about experiments, vision, audition, and natural language understanding. And we talk about a little more and more practical things. Basically, we say FGP platform from a little startup that I helped to create called the Genesema LLC. The Genesema is coined from the acronym we talked about it. All right, suppose we have a controller, right? Then you wear the cell phone. You wear the cell phone, and the cell phone, and you have a controller as a joystick. Then the camera, your camera are mounted on the cell phone. Then you can really, it's like a baby, a virtual baby, wearable baby. You take the baby out for a walk to play so that it learn through lifetime. This particular example, we say support the output is disparity. You have twice, you look at, hey, you want to see how far that is, all right? Then the how far is represented by disparity, then through epochs. Through the epochs, for example, that we have a frame number, all right? 100, 200, we have 700. Then you can see that the accuracy is about over 1 pixel roughly. This is a top down. You really need a top down. In this case, 0, 1 is good for, is better than a 0 top down, all right? So you can, this is the first system that reported for disparity and texture and photometric information all combined to output disparity, all right? Not based on the correlation. This is the first time. And it will be robust, will be better than correlation-based disparity detection, which will have this degeneracy when you have uniform regions, all right? We don't have this problem, all right? And we will have like weak texture, we have uncertainty output, and we will also have multiple patches that put together, the integration takes place together, all right? And look at the consciousness. And I will not talk about too much about consciousness. It's a very exciting and topic, but it's very heavy. And I suggest that you take a look. I posted June the 9th, 2020. And so basically, I proposed a model for consciousness based on autonomous programming for general purposes. So conscious intelligence requires auto programming for general purposes. And I think as long as you have motivated autonomous programming, you have a universal Turing machine Genesema universal Turing machine, then you can show consciousness. So intelligence with consciousness or conscious AI is coming. That's my prediction, all right? We have not reached to that point yet, but theory is ready. Now talk about Brain Mind Institute. And in order to really learn this exciting future of AI, and I think that we need a new kind of education. And Brain Mind Institute that I helped to create, it's a nonprofit organization, is meant for that. And we later on, we also have a AIM context. And if you go to the website, and it talks about why BMI, why you need that. And you also have classes like I will talk about classes, and we have also context. So classes, we have cognitive science, and we have automata theory, because people in control, many people in neural networks are from either control or physics. They have not learned automata. So I think automata is very important. And then I have a book that I wrote. And I put it out. This is a second edition already, and it's available in the BMI site. I will find time to put it on Amazon. Right now, it's not in Amazon yet, and will be soon. So use this textbook for 871. Then each course we have video lectures, PPT file, exam each week, and if you pass, you have certificate useful for your resume and future research. And we also have a context, because we don't encourage the people that try programming and the data. And so we start from 2016. The first prize is $10,000. Thank Genesema for donation for the prize money. And it's unique. No contest like that. It's a task independent, modality independent. When you do tasks, you don't know what kind of task you are doing, right? So you really need to do task-specific learning. And for full-time student, we reduce the price. For 150, you can have 3 courses, you can attend the workshop, and you can have 1 entry on the contest. Genesema little startup will provide hardware and software for APFGP. It has 3 models. 100 is a learner model, and 50 and 40 is a performance model, because many people probably don't need to train network, just do performance. Autonomous Programming Operating System, AOS, is for people can use the DN as a engine without really doing programming. We have a user interface ready. And 3D Tube is a social network for 3D content, so that you can record, you can post your 3D content, either video or images, 3D video binocular onto the video side. And 3DI is a vision system, and later on we'll teach vision system for disparity detection, for navigation, for object recognition, and so on. Prototype is ready. Now, in conclusion, APFGP has been mathematically proven using a constructive method, and early experiments have been used, tested on 3 bottleneck problem of AI, vision, audition, and the natural language understanding. Genesema UTM is learning by DM. It's a general purpose and fully automatic inside the skull. Neural network community is in crisis, but if we look at this method here, and the crisis will be over, but it depends on whether you are open-minded or not. You can stick to the traditional AI until it's too late. Natural intelligence and artificial intelligence have been unified by the APFGP theory. That's kind of exciting. And many people don't believe that, John, you're lying. How can you solve the brain problem? I'm not talking about we solved all the detail. I'm talking about the first order model based on APFGP. Nobody I know that reached this breadth and depth, right? Nobody. Very thorough in terms of theory and experiment, and nice properties, and optimal. And a conscious machine will arrive. Thank you very much. Thank you very much for attending.